GM and G Eigen, Bo, what is going on? Welcome. Today we are going to be talking about hyperscaling interop capacity.
Welcome to EigenLayer Unlocked, an interactive educational journey through the EigenLayer ecosystem created by technical founders and builders for the entire crypto community. A special thank you to our partners, AltLayer, Polymer, Authentic, Skate, and Lagrange for helping to make this happen. Our goal is to raise the collective knowledge of the EigenLayer AVS ecosystem and unpack the technical designs of the top teams in space. Welcome to EigenLayer Unlocked.
G Eigen, GM and G Eigen, Bo, what is going on? Welcome back to the show. Today we are going to be talking about hyperscaling interop capacity and all of the integrations that you guys have with EigenLayer. And as always, thank you for the support. You guys are the main sponsor for the EigenLayer AVS series, EigenLayer Unlocked, and we're very grateful for your support and very excited for this presentation. So without further ado, Bo, here we go.
Yeah, happy to be on the show. Really excited about the topic today. I'm talking about how we're working with EigenLayer to scale interop capacity. I'm going to define what interop capacity means and what the result of working with Eigen is. So I just do like a quick brief intro on myself. I'm a technical co-founder at Polymer Labs. I previously worked in Web 2 as a database engineer across a number of different startups, mostly on the infrastructure side. Love databases, now love blockchains and Interop. So interesting transition there. Cool. So the lay of the land today, from my perspective, is that we have a lot of applications that exist on chain that kind of sit at this intersection of regulatory arbitrage and social coordination. And this intersection represents, a tiny subset of the total possible applications that could be built on chain. And then this begs the question of how can we make building on chain the best option for future applications in totality? So I try to break up this problem into 4 quadrants. It's a bit of a simplification, but bear with me. The 4 quadrants are network effects, time to market, performance, and cost. Time to market is important because a startup needs to survive. They need to get to launch. The faster they can get to launch, the more attractive it is to build with a certain set of tools or in a certain ecosystem. The network effects or platform effects represent the distribution problem. So it's the question of, if I build for Apple's Apple Store, will I get maximum distribution versus building somewhere else? AWS's marketplace and a few other marketplaces also represent this. Performance represents the question of, can I build an application that is competitive with other applications in my category? And cost is pretty straightforward. It answers the question of, if I build this application and this application scales to perhaps millions or even billions of users, can this still be a profitable business for me? Cool, let's jump into each of these categories. So for the time to market quadrant, we can see that if you have a lot of application building blocks or application primitives, it can drastically reduce your time to market. In Web 2, you have a number of software as a service APIs, so many different things, infrastructure primitives, application primitives, different types of APIs for information and other things that you can build off of to speed up your time to market. And in Web3 in the future, the hope is that we're able to build application primitives that can help future applications get to market very quickly. For example, if we bootstrap a driver marketplace on chain, it means that applications building on top can leverage this existing marketplace primitive versus having to do all the bootstrapping work themselves. And there's a lot of bootstrapping waste that happens in Web 2. It takes a lot of funding and a lot of human and social capital to get a lot of these platforms off the ground, especially a lot of these dual-sided marketplaces. Execution and data capacity affects performance and cost. The supply and demand relationship means that the more execution and data supply that we have relative to demand means that the cost will come down. And the more execution capacity we have, applications can scale their app both vertically and horizontally across many chains eventually. Next, we have interop capacity. This influences network effects, performance, and cost as well. So 3 quadrants. Its influence on network effects shows that if you have if a builder builds within a specific ecosystem or with a specific technology, if they have the ability to leverage application building blocks that don't exist on the same chain, on other chains, or maybe even other remote ecosystems, that improves the network effects of building on chain. Whereas for performance and cost, the latency, cross-chain latency of an application affects the performance, while the overhead of the cross-chain interaction will affect the cost or profitability of the application as they scale to hundreds of millions and potentially billions of users. Lastly, we have latency. Latency affects the performance of the application. For example, over 10 years ago, Amazon did a study showing that for every 100 milliseconds of latency added to their application, they lost 1% in sales. This translates to, in today's terms, billions and billions of dollars in lost revenue per 100 milliseconds. And you see this trend happen across other types of applications as well, not just in e-commerce, social media, search. The drop-off rate when you increase latency is tremendous, which affects user attention and profit to the application ultimately. So to make building on-chain work for all apps, we must improve in all 4 quadrants to be competitive. The applications of today need to drive improvements across these quadrants that enable the future applications of tomorrow. So where we're at today, we can support protocols like Story, which can build what they need to build using a single app chain optimized for their particular workload, meaning that they can unlock or create this massive IP graph with thousands of layers for their specific use case. But the issue is Story today is still orders of magnitude in terms of scale removed from what Uber operates at. So an Uber runs on 20 plus different building blocks or database systems on the back end. Each of these database systems, you're going to be looking at hundreds, if not thousands of nodes on really high hardware specs supporting these systems. Just their analytical database alone processes over, or their analytical backend processes over 100 plus petabytes of data within minutes. This is a completely different scale than we're dealing with in Web3 today. And next, I really want to dig into how we can improve in the performance and cost quadrants to make building applications like Uber on-chain possible. So where are we at in the scaling journey on Ethereum? Well, the good news is that we're currently scaling execution, data capacity, and latency. So EigenDA recently ran an experiment where they processed over 15 megabytes per second, or all the raw block data from 15 plus chains simultaneously. This includes chains like Bitcoin, Ethereum itself, Solana, CeLo, Celestia, Avalanche, and so on. And on the other hand, we have projects like MegaETH, which are scaling execution capacity and latency. They can do over 100,000 TPS with 1 millisecond block times. So as we scale all this execution, data capacity, and latency, we also need to scale interop capacity across these chains. And this is kind of where Polymer comes in. So in this diagram here, we show that Polymer is responsible for scaling the verification capacity, while we leverage EigenDA to scale the data capacity of our product. And I'll get into the definitions next. So what is interop capacity? Well, we can define interop capacity as the maximum amount of verification and data capacity that a protocol can handle, where verification capacity is the overhead of the verification logic and the protocol logic for the interop protocol. Different interop protocols have different features. This results in different levels of overhead. Different security models have different verification costs, which also affect the overhead. The data capacity represents the packet, proof, or signature data required by the protocol. Packet data is required for the actual payload. Proof and signature data is required for the various verification modes that an interop protocol can support. Interop overhead is then defined as the amount of interop capacity that's utilized to achieve a certain level of latency and security. And we can see this relationship between interop overhead and latency in this chart here. So on the far left, we have proving layer 1 to layer 2 settlement. In the middle, we have a Lagrange state committee. And then on the far right, we have a sequencer P2P verification mode. And we can see that as latency goes from high to low, interop overhead goes from low to high. So the faster you go, the more interop overhead you incur. Let's review the different types of connectivity modes here. We have a sequencer P2P verification mode, where verification happens over a peer-to-peer network. We have a Lagrange state committee, where a committee of nodes attests to the valid execution of a rollup after data has been published. And then we have the rollup native bridge, which represents rollup settlement to Ethereum. The sequencer P2P has latencies of between as low as 2 seconds, or as low as block time is as low as a block is produced and gossiped over a network. A Lagrange state committee has roughly latencies of 15 to 60 minutes. This really depends on how often a rollup publishes data and how fast that data finalizes on Ethereum. And the rollup native bridge can take anywhere between an hour up to 7 days. This really depends on the mode of settlement of the rollup, whether that's using ZK proofs, whether that's using an optimistic fraud proof, and the size of the length of the fraud proof window as well. Okay, cool. Let's look at the data overhead of each connectivity mode using Base as an example. So for the sequencer P2P client, we see that this takes, every 2 seconds, or at the 2-second connectivity rate, takes 7.5 kilobytes per second of data, or 648 megabytes per day. For Lagrange state committee, which operates at roughly every 15 minutes, we can see that this takes 675 bytes per second, or 58 megabytes per day. And for a rollup native bridge, which operates every hour, we can see that this takes 2.7 bytes per second, or 233 kilobytes per day. And what this translates into, well, let's review the data bandwidth on Ethereum first. So the data bandwidth on Ethereum is roughly 5.5 gigabytes per day of blob bandwidth. This is based on the blob size, Ethereum block times, and number of blobs per block. Currently, we're sitting at roughly 36% utilization of this data bandwidth. Where is data bandwidth utilization heading? Well, projects like Base, Optimism, and others are currently increasing their, target gases over time. And this is with the goal of, and Base has this goal of getting to 1 gigagas per second on Base. They started with 2.5 megagas per second back in March. Currently, they're already pushing it to 12 megagas per second, as you can see in the update below. And this trend is expected to continue. So we expect that Ethereum DA will be properly utilized soon, probably to the excitement of many ETH folks and ETH holders. So the issue with Ethereum DA is that we can only support a small number of chains over these various connectivity modes, especially the low latency connectivity modes. ETH sits at 5.5 gigabytes per day, and this accounts for current utilization rates. So over sequencer P2P, we can support up to 5 chains, or approximately. With the Lagrange state committee, we can support 60 chains, approximately. With the rollup native bridge, it's a little bit better. We can support 1,500 chains, but obviously there's trade-offs between latency here. Now, what is the data bandwidth on EigenLayer? Well, we have 1.3 terabytes of data availability bandwidth per day currently. This means that EigenLayer can support a much larger number of connected chains. We can support over sequencer P2P over 2,000 chains. With the Lagrange state committee, we can support 22,000 chains, while with the rollup native bridge, we can support an egregious number of chains, 5.5 million. Hopefully, we do get to that number one day. But it's going to take some time. And the important thing to note here is that the number of chains that are connected in real time increases the network and platform effects of building on-chain. When a building block is more accessible remotely, that increases the usability or composability of that building block. So we want to get these latencies down, and we're only able to do so at scale by leveraging EigenLayer. Let's look at verification overhead next. So what is the verification overhead of connecting 100 rollups using a peer-to-peer protocol or a point-to-point protocol? the sequencer P2P client or verification mode results in a cost of $155 million per day. This is egregious. Lagrange State Committee results in a cost of $1.9 million per day. The rollup native bridge is more, I guess, practical in this sense. Like you can do approximately like with $40,000 per day.
Can I hop in and ask a question here? Because is there anyone that's using, I mean, let alone point to point model? Is anyone using like the Lagrange State Committee and or the sequencer point to point model and paying $155 million a day?
No one is using the sequencer point to point model. I think anyone would look at that cost and be like, this is just not practical. We're not going to do this.
Okay.
The Lagrange State Committee, there are a few integrations that Lagrange has. I don't believe the volume over those integrations. I don't know what the volume is over those integrations today. Yeah, so that's a question mark.
Okay.
And this would require Lagrange State Committee update every 15 minutes, and this like factors in like the data costs and everything associated with it as well. So my understanding is that there's a difference in the way some protocols are using Lagrange, and there's a difference in, I guess, how much volume is flowing over that protocol, which results in like the number of updates and so on.
Got it. And then even down to the rollup native bridges per day, how are those costs paid? Are those gas costs that say, an Optimism native bridge, Optimism is paying this execution overhead is paid in ETH to the Ethereum validators?
Oh, actually, this is not the settlement cost of the rollup. Sorry, I should clarify. The rollup native bridge is using the already settled rollup state on Ethereum and proving that on a connected rollup. So this is literally saying like, okay, this rollup already settled. Let me prove that some event or something happened, like a message event was emitted on this rollup that's connected over Ethereum, because every rollup has access to Ethereum state already. The cost of this is the cost of those proofs.
Got it. Okay.
Yeah.
Okay. Cool.
And like very few people use like rollup native bridge for anything. And the way a lot of rollup native bridges work today is that you make a write to the rollup, you make another write with the proof on Ethereum first, and then you make another write on the other counterparty rollup. At Polymer, we do support verifying packets sent over the rollup native bridge directly without having an extra write to Ethereum. And this is kind of like factoring hypothetically what that could look like, even though I don't believe anyone is doing that today.
Okay.
Yeah. Cool. Now let's look at the execution overhead across all these 100 rollups using Polymer. With the sequencer P2P client, the costs decreased dramatically to $30,000 per day, which is why we have a separate chain for this, or L2 for this. The Lagrange State Committee costs come down to $686 per day, and the rollup native bridge comes down to a very digestible $4 per day. Very, very, very cheap. Let's look at the reasons for this massive cost difference. So the reasons aren't just that our chain is optimized. There's fundamental reasons for why there's such a big cost difference. There's a difference in connectivity model. So if you compare the connectivity model of Polymer, which is an L2 or rollup hub and spoke model, with a point-to-point model, you can see that the point-to-point model, all-to-all connectivity, comes with a certain level of overhead. The hub and spoke model does make that connectivity more efficient, and especially more efficient at scale, where you have a lot of chains, and a lot of chains are communicating very frequently with one another. The other thing is that there are currently extremely high profit margins for optimistic rollups. So you can see that Base is currently operating at a 98.5% profit margin. This is taking the cost that Base charges for execution and subtracting the costs to Base, or the expenses to Base, for settlement to Ethereum. This means that if you funnel verification logic directly to Base instead of offloading it to a hub and spoke model like Polymer, you end up paying these margins, if that makes sense. Polymer can greatly reduce these margins, optimizing for the verification costs of a lot of these models, and also by optimizing how performant we are for that particular workload. let's step back a little bit and talk about the practicality of building on-chain versus building just in the cloud or just a regular web app or Web 2 application. If we compare the cost of sending a packet across rollups versus the cloud, currently across rollups in production on a production point-to-point interop protocol today, it can cost roughly 25 cents per packet. Whereas if you send a packet in the cloud across availability zones, and this is the more expensive cost, there's like intra-availability zone costs, which are a little bit cheaper. So looking at the more expensive network costs in the cloud, you get approximately like 0.000007 cents per packet. And this is a 357 million times difference in cost. And like when you look at this number and you like put yourselves in the shoes of an application developer, like basically trying to decide whether or not they're going to build on-chain in the first place, this is a number that just doesn't work for them. Because any application at scale that handles like millions of users and potentially billions of users, especially these like real-time applications that have real-time requirements to be competitive in a market where there's a lot of different apps, what it means for them is that if the answer to their question of like how much is it going to cost me to scale to like a million users or go from a million to 100 million, that it's going to be 357 million times more expensive to scale horizontally, it just makes building on-chain a no-go. And this is one of the main problems that Polymer wants to solve to make building on-chain practical. So if we're able to solve this problem and get these costs down, what could the future look like? This is a diagram of what a microservice-based application in the cloud looks like today. You have an application API, which routes over a few microservices. You have a few different databases. You have a queuing service. You have a message queue in Kafka. You have some background services that does some data processing, probably for some analytics. This is roughly what it looks like. Usually, it's like much like larger scale than this. I think at one point Uber had more microservices than engineers, which is absolutely ridiculous. Not all of them were like well maintained, but like you get the picture. So what does this look like transitioned into the applications of tomorrow? The microservices could become rollups. The background processes could become AVSs, and the message queue could become Polymer, with all of this settling down to Ethereum. And to really be able to enable that architecture on chain, we need to be able to scale a lot in those two bottom quadrants that we highlighted earlier in performance and cost to make internet scale decentralized applications possible. And this is an invite to folks to build with us towards infinite connectivity and beyond. We have some links to Polymer. We have some personal links for myself, for my Twitter. Feel free to reach out directly if you want to build with us, or if you're just interested in discussing some of these topics that were presented in the presentation.
Awesome. So the main goal here is to bring the performance and scale of building on-chain to the level such that it is comparable to the cloud.
Yeah, exactly. Although I'll caveat that it likely will never be better or more performant, but that's fine because there's 4 quadrants there. There's the network effects, there's the time to market. As we get more app building blocks, time to market becomes better, especially for certain categories of applications. And as we gain like a larger user base, more liquidity, more other things, the platform and network effects, like the distribution effects of being on-chain become very digestible too. As those 2 quadrants improve, it actually helps like application builders digest some of the increased costs or performance penalties of building on-chain. But the gap between those two cannot be too large. And I feel like the gap today is just way too large of a chasm. We just need to bring them closer. It's fine if they're never as performant. That's okay. But it needs to be a little bit more balanced.
Yeah.
Or a lot more balanced.
And the reason that we've heard to, why it may never become cheaper or faster than building in AWS or the cloud is because this is inherently a decentralized system. And in order to derive that property of verifiability, we need multiple different nodes. And so on the one hand, in a cloud format, you could coordinate with just one maxed out mega node, right?
Yeah.
And that would be okay, but you'd have to trust them, and they could increase the scale and the processing scalability and efficiency, but the capacity is much higher because they don't have to coordinate amongst different nodes. But as long as we want to derive that property of verifiability, we have to coordinate in a decentralized way. That'll have the benefit of verifiability, but it'll have some cost in latency and efficiency.
Yeah, I
Mhm.
actually think that that we can get the execution costs down to pretty much cloud level. I'm really bullish on the idea of, or the design space that Mega ETH is exploring. Like, why can't we just have like centralized execution environments where we like max out hardware specs, and that gets you like as close, or like pretty much like very close to the performance of just a regular web server. The one difference in my mind is like the data costs. It's very difficult to get the data costs exactly as it were with a traditional database, because a lot of these database systems, they're working with like a replication factor of like 1, maybe 2. So it's like, yeah, I have like a like hot backup or something for my database where I stream updates to. That's very different from a data availability network. Like you can get the costs like close-ish, but like the DA networks, they have certain like encoding schemes that they have to add on top. There's this overhead and like gossiping data. I think EigenDA is exploring interesting trade-off space there, where they're like, okay, like screw the P2P network. We still have to pay like the encoding costs, and so like disseminating the data, but we won't have like this like P2P coordination layer between our nodes, which does improve the performance a little bit. Can theoretically get us closer to that cost of like just a single database with a single backup.
Got it. Yeah, so that's interesting to hear. Execution overhead may come down, but it's the data bottleneck that is the main limiting factor
Yeah.
with relative to cloud. I want to don't like kind of dive in on that a little bit. So I'm gonna hop back a few slides here. Let's see. Let's see. I think it was. I want to get back a few slides here because generally, I think base is actually a good example here. And here's the data bandwidth. This is the main bottleneck. So we had a podcast conversation with Justin Drake not long ago, and he mentioned how he actually, there was a lot of back and forth with him and the benefits of composability. And then they on a podcast, he looked at base, right? And originally the idea was that base's revenue was primarily, and I think you even had the revenue on here, maybe in the next slide. I want to find it because I think you did have like their margins were.
Oh, it's in the execution overhead slides.
Okay.
I'll pull it up.
Okay.
This one.
Yeah. So their margins here, 98%. They're making $86,000 a day. Like this works out to, a couple $100 million per year. And the discrepancy was that, Justin Drake was saying that almost none of that came from MEV. Almost all of that came from execution overhead and gas costs, right?
Mm-hmm.
But it turned out that this wasn't the case. It turned out that most of this was coming from MEV because every time base ends up running into their congestion limit, they end up raising the gas limit. And so, the MEV is maybe here and it stays there. And then congestion fees will rise. But every time they start to rise too much and surpass the MEV, they end up knocking the cost back down by raising the gas limit. And every time they raise the gas limit, it kind of adds more data bandwidth, right? So like how are they able to just, raise the gas limit? Is that just abundance? Like can they just continuously raise the gas limit and not force their users to pay significant congestion fees? Eventually they're going to reach capacity, right? And they can't just keep raising the gas limit in perpetuity.
Yeah, they're gonna hit the DA like bottleneck. The other thing that people talk about a lot is state growth. We don't need to get like too deep into the state growth problem now, but yeah, state growth is definitely an issue. There's like solutions to state growth, but it's a really tricky problem when you have like a generalized compute system where there's a lot of different apps and ever growing number of apps. and the way those apps are utilized, or the utilization patterns of those apps, is just very different. And there's a lot of like user accounts, some of them real users, a lot of them probably aren't real users. Um, the stakeholder problem is very real. Uh, there's like some like temporary solutions to that, and there's some like long-term solutions that folks are working on.
Got it. Okay. Um, that makes sense. So generally, you see that the data processing bottleneck here is our main limiting factor when we're trying to get to cloud level scale.
Yes.
And and with that being the bottleneck, why do you think Ethereum is not at capacity? Like the blobs aren't filled up, utilization rate, isn't 100%. Why do you think that's the case, given that, that's the main bottleneck, but it doesn't seem like we're hitting it yet?
My thesis is that we already started with like a limited subset of applications, and then we took this like limited subset of applications, then we replicated these applications across all these different chains. I think that in order for us to truly like, I guess, break through to all the, because now these people talk a lot about like infra not having customers, we have too much infra. To really break through that problem, it seems like we need to expand the scope of the type of applications that are built on chain. And then we kind of have this a bit of like a chicken and egg problem, where like the performance penalties and the cost of building on chain suck. Like they just suck. And but then on the other hand, like if you don't incentivize folks to even build these initial apps, this is kind of where like incentives and other like crypto economic things do come into play. That if you can't get people to build these initial app building blocks in the first place, it doesn't make sense for future builders to build on chain, if that makes sense. So there's a bit of like a chicken and egg bootstrapping problem, where like we need the first two quadrants to really level up to help the bottom two, and we also need the bottom two to level up. When the bottom two levels up like a little bit faster than the first two quadrants, then we end up in a situation where there's too much infra, and like where's the demand, and like ETH price goes down, ETH bad kind of sentiment.
So the last 3 to 4 months.
Yeah. Like the last 3 to 4 months of like the world is falling apart, and like Solana's winning because they're targeting use cases, if in theory, or so people like claim on Twitter, and like I can't validate this because I don't follow enough of these projects, but claim that like they have other, or people exploring other use cases beyond just like meme coins and DeFi.
And speaking of Solana, do you think like if they are more consumer facing, and so they claim, and we end up getting a lot of applications that do really, really well, but are only on a single chain, those don't necessarily lead to more demand for Interop? Or right? So if that's the case, do you see this evolving in such a way that we end up with high levels of composability, applications on bunch of different chains, and we're doing these more like atomic transactions and super transactions that occur on multiple different chains? Or do you think there's going to be a few general purpose rollups with a few killer apps on each of them, and people that are on like in these ecosystems will stay in these ecosystems?
Yeah, I guess the way I'll frame this is, imagine you put, this is not going to work. Like Amazon runs at like an insane scale. They have an insane amount of hardware backing their internal system. So this wouldn't work in practice, but I'm just going to propose this like hypothetical situation. So like imagine you put Amazon on Solana, and Amazon's like, okay, in theory, like Amazon, all of Amazon's compute runs on Solana. You can like buy and sell in this marketplace, and everything's on Solana. But the issue is that there's a minimum like 400 millisecond bound for a transaction. Like you can get the inclusion rate down. They talk about like multiple concurrent proposer and like all these other things, but the execution latency is still going to take 100 milliseconds, if not seconds. I think it takes more than like seconds to actually like get to see if a transaction failed or not. That's just not good enough for Amazon. Like at the very least, Amazon's going to lose 4% of their revenue, which is going to equate to probably like $20 billion a year in lost revenue. And this is not practical for them. And once you get to seconds, it's like, it gets even worse. They're losing like hundreds of billions of dollars. And my take is that, and this is the reason why I like the design space that MegaETH is in, is that latency matters. Like there's so many applications that already exist off chain where if you're entering like DeFi is a little bit different, right? Like DeFi is a new category. If you're entering a new category, your performance is not great, that's fine. If you're entering the existing category and your performance sucks, you'll never make it in the first place. To give an apps a fighting chance, they have to at least not be super handicapped. And the performance of the application and the cost of running the application on chain are huge, like massive handicaps. So if you like shoot yourself in the leg and you try to run a race, like you're probably not going to win this race when everyone else is already running at the speed of Usain Bolt. Like there's a bit of a gap there, I would say. So I think long term we'll see a lot of like localized rollups, meaning that we'll see rollups that are deployed in specific regions, where to power a real time application, if you're accessing that application from Singapore, you're probably not going to be writing to a node in New York. If you're accessing the application in New York, you're probably going to like do writes essentially locally on your like local rollup. So maybe there's a future where there's mega ETHs in every region, where an application is actually split across all of these rollups to deliver the right kind of UX to be performant within its category.
And so if we cycle back to like one of these earliest slides where you illustrate the trade-off, and we have
which one?
The essentially that this one here, like basically that the amount of overhead scales with as we lower latency. There's also like a geographical regional component to this, is what I'm hearing.
Yes.
And so we can actually load. I mean, how do you think about geographical location in terms of this dichotomy between overhead and latency? Where does the regional component fit in?
The regional component fits in the far right of the diagram. So I would imagine that if you have applications that want to optimize for UX or the user experience of using their app, that you would have very low latency communication in localized clusters of rollups. So if I'm building off a building block, like let's say we have like a real-time building block, like a rider and driver marketplace, just a primitive, not like any of the ride-sharing application logic on top or anything. So just this marketplace alone, this marketplace would be split across geographically naturally anyways.
Mm-hmm.
And then you would imagine that there's like a bunch of applications building on top of this marketplace. Each one of these applications, whether they bootstrap a rollup or whether they build an application on an existing rollup, those are like, two options that they can take. They're leveraging this real-time marketplace to perform their application, I guess like functionality. And there's going to be a lot of communication in real time between these rollups together. So I'm imagining in the future, communication will look like the cloud today, where there's a lot of like very like dense, like heavy network utilization within like availability zones, within like server racks, and then across it, because the price is going to go up too across like AZs, and like with like the distance, and whether you're paying the cost in latency, whether you're paying the cost in other forms, it does come at a cost. So I would expect less network traffic between between clusters of rollups, even regionally, and then across regions you would see even less network traffic. So like we're trying to build a system where we can enable this like really high throughput, dense connectivity between rollups that's very, very frequent, very, very high rate, and make it as cheap as possible to make these like types of applications practical in the first place.
Got it. And practically looking at the Polymer AVS, maybe we could hop over to that slide.
We don't have a AVS.
No, but the way that you guys work with AVS is there was a slide.
Oh, okay.
Here. So, you kind of described this Polymer.
Oh, shit, sorry.
Sorry. This messaging queue, right? And then this is like the queue that the AVSs are running through the tasks in this queue. The way that you guys are submitting these messages to like the very densely connected clusters of rollups. Could you explain generally how? I think at a high level in theory, I understand that there's like the dense connectivity of these rollup clusters, but how does that work when you guys are submitting these messages to ultimately to the AVSs or down to Ethereum?
Yeah, so my mental model for this, and obviously this is just conjecture here, is that Polymer in my mind is very similar to Kafka. So Kafka is a messaging queue. It's open source. It was the Kafka team at Uber was probably the most leveraged team across all infra teams. So many teams relied on the Kafka team for their services. And I believe Kafka at one time, which probably was processing the most amount of data across all these services, because when you have a system where demand is kind of like up and down, up and down, up and down, you want, I guess, like this like message queue or buffer in the middle for handling additional load, meaning that like if rollup 2 can't keep up with rollup 1, you can have some backup for some period of time. Now, once utilization comes back, rollup 2 can start like processing the backlog and do what it needs to do afterwards. So a lot of like microservices that I'm familiar with heavily leverage this design pattern of putting like slapping a message queue in between everything and just making everything async, so that like under normal circumstances there's never a backup, but if there is a backup, these messages are not lost and they're stored somewhere that's verifiable.
And that's the messaging queue.
Yeah, exactly. And that's kind of like my mental model for Polymer.
Okay. Okay. Um, and so Kafka, um, that's something honestly I didn't hear until this presentation. Like I was unfamiliar with it. But Kafka in the general cloud architecture are these messaging queues between microservices.
Yeah, that's how most people utilize them.
Okay. Okay. Very cool. And so when you're looking at like some of the different interop solutions out there, um, and thinking about like scaling interop capacity, um, I'm trying to I have this question in mind, but I'm generally curious how you're thinking that this is going to expand as we so
Mhm.
what I'm taking away is basically that your thesis here is we're going to continue modularizing. We're going to
Yep.
continue to get more and more microservices, and then Polymer is able to fit as this just generalized messaging queue between these different microservices.
Mhm.
Um, when when you guys are building Polymer, are you doing a specialized queue for like microservice A to microservice B? That path has its own queue, and then like service B to service C has a different queue, or is everything generalized and like everything goes into one Polymer queue, and A to B to C to D, all of them, all of the messages that are going between them go into this one generalized Polymer queue?
That's a great question. It gives me an opportunity to show IBC. Um, so, so with IBC under the hood, we can support. IBC has this concept of channels, which means that you can authenticate a queue between two services, so that those two services may own that queue themselves, and no one else has access to it. Then those services can then like send messages over their like own queue that can be processed in parallel to everything else that's going over Polymer. Um, People aren't forced to use this. We're actually planning on supporting other forms of interop with our system. But if they want to use IBC semantics, they can do what you described with those IBC semantics.
Got it. Okay. Okay. That's very cool. Yeah, I think IBC is like, something that everyone knows and loves, but like just you guys are helping to like bring that to the world. I think my last question here in a little bit deeper into the EigenLayer integrations. Um, you've got kind of like the couple of arrows here between rollup 2 goes through the messaging queue of Polymer, and same with rollup 3 goes through Polymer, and then ends up to AVS1 here. So what exactly are you guys using these AVSs for, or this EigenDA? Like, what is the nature of the integration with EigenLayer?
This is just graphical in nature. So the services that a rollup will use, since I kind of see AVSs as providing these like software as a service APIs, similar to software as a service APIs in the cloud. Um, it's really up to the AVS themselves. I feel like there's not enough AVSs to really like, and enough rollup microservice to really craft a story for this at this moment. But I would imagine that this is roughly how it will evolve, where like these AVSs will provide these APIs that rollups can use. Obviously, the rollups can use it directly as well, but
Mhm.
Polymer kind of provides like a messaging interface type API for that interaction. Um, and then it would evolve from there. So like if the AVS perhaps is doing some sort of like verifiable background processing. I'm making this up right now. So some verifiable background processing of like the historical state of the rollup, so that it can inform some like AI agent to like take some sort of action upon this verifiable data. So the AVSs could be like Lagrange, where they like crunch some like zero knowledge proofs to do some like data analytics. So there's like this long running query over the rollup state that then can get fed into some like AI agent that then does some like rebalancing of some DeFi protocols, like liquidity pools across all these different chains. And maybe that's the future that we'll live in.
Mm. Yeah. Okay. That makes sense. Another one, just because we've been hearing a lot from some of these AVSs, and I had a conversation with Predicate yesterday, and they're doing some of these. They're doing like pre-transaction checks.
Yeah.
And so like, one thing is like KYC, for instance, like making sure, they have some like data providers who, are going to check like OFAC lists and
Yeah.
anti-money laundering, maybe KYC. If they were to have some sort of queue of transactions, you would be able to hook like these roll-up microservices up with their API. Their API would basically like check each of these different tasks, and then you would service the queue of transactions and make sure that they execute appropriately based on the checks that they get, and whether or not they pass.
Yeah, it would be probably like two different ways to interact. One method would be that they just have or build integrations themselves, so that they understand the transaction format of all these different rollups, meaning that they basically take the transaction, inspect it, like basically act as like a screen before submitting like the post screen transaction to the rollup mempool. This doesn't stop like someone else from submitting a non-screen transaction. So like I'm not exactly sure how the system works to like handle that case. Another case would be like hypothetically, like if the entry point to the system was their rollup or chain or however their system exists, then if Polymer were to link that to the different rollup, they could perform the screen on chain and then issue an action over Polymer messaging to the other rollup, and that action would already be post screen and authenticated, so that the application on the end knows that okay, this is from Predicate. This interaction is already a pre-screened interaction. I'm going to accept it.
Got it. I mean, I'm getting very, very excited. This happens every time we do one of these educational series, because it's like, we explore these really, really deep ecosystems, and I'm learning that EigenLayer is so early in the nature of like you said, there's only a handful of AVSs on there right now. We
Mhm.
we haven't even scratched the surface with how these microservices are going to evolve. And then, there's opportunities to connect all of these services with one another, so that, we can get fast finality and ZK and Lagrange state committees, and they're all pulling information from on-chain and off-chain sources. And then, all of this is very, very deeply connected. I think we've gotten this explosion of infrastructure. Now all of that is out on the table, but we haven't been able to connect this infrastructure so that it can work together, ultimately providing a better experience to app builders, and then uh, to consumers of these apps as well. Um,
Yeah.
yeah. So you guys are one of the ones that, you're not building one of these microservices yourself. You're building, the connectivity between these microservices, which I think is just as important, if not more important. So yeah, this
Yeah.
has
And
been.
and
Mhm.
yeah, we'd love to add some points on the connectivity front. I think a lot of people like don't understand like where we stand in the space and like what we're focused on. Our primary focus is on what we described here, like trying to imagine this world where you have like low latency interactions, like high density interactions across like clusters of rollups that are deployed to like specific regions. And these rollups are like, imagine like immense scales. These are like 1 million TPS. They, they do like, or like producing blocks every millisecond, or even potentially even faster than that. Like basically trying to support these real-time applications, and really trying to like think in that mental model of how can we take that cost, that 357 million times more cost of sending a packet, really get that closer down to like a small multiple. And like this kind of would be a big unlock for this space. And because of this architecture, we're very focused on rollups, very focused on rollups on Ethereum. We have a number of innovations in the, I would say like on the safety front of how we conduct cross-chain interactions that are very interesting. We're actually I'm working on, and we'll soon release a rollup improvement proposal around this concept of rollup contingent transactions. This is a specification for how to conduct cross L2 communication based on a shared understanding of the mutual L1 history across these rollups. So where the contingency comes in, it's on the L1 state itself. So it's trying to establish some safety invariants for what's safe communication, what isn't safe communication, how do I conduct safe communication, and we're trying to like push for like industry-wide adoption of these concepts and these security and safety primitives.
Epic. And so you imagine that rollups will implement this, and then when we're doing some cross rollup transactions, then we'll have a more consistent process for reading the L1 state and conducting those transactions across rollups.
Yeah, so the requirement on the rollup side is for them to track their L1 origin or their L1 history. And the requirement on the Interop protocol side is to perform contingency checks around this shared L1 history across rollups.
Wow. So you're not one of the you're very much in the async camp for Interop.
Yeah, I'm very very much in the async camp. Just because like I feel like having like worked in like Web 2 and seen the amount of scale or just the sheer amount of hardware it takes to like run these types of businesses. Um, it- I just can't imagine putting all that on a single computer. Like it just like it doesn't like people say like, oh yeah, I can just up the hardware. I'm like, you have to realize like these companies run for each database system they have, every single one of these database nodes is on maxed out hardware. And there's like hundreds of database nodes, thousands of database nodes, many different clusters of these nodes just to support one team. And it's like it's a ridiculous amount of hardware already. So like it's just like, how do we on a single like reduce all that to a single like maxed out hardware node? Like it just like doesn't make sense to me.
You just can't compress the amount of data that much.
Yeah, exactly.
Fascinating. Cool, man. I mean, is there I feel like we've had plenty of conversations, and I all of these interop providers are just continuing to like dive deeper and deeper into different solutions. And I think, a lot of this, there is a very common goal, and everyone's approaching this problem from a few different angles. And so appreciate you guys kind of taking like this old scale approach to it. And I think it is different from a couple of these other interop providers, but you guys have a very vibrant vision that I hope to see play out.
Yeah, I mean, I very much want to see this play out because I think if this doesn't play out, then it means that the Web3 as a whole probably is going to be stuck with like a subset of applications and not be able to service like this like much larger, like grander vision of like bring the whole world on chain that a lot of people talk about.
Yeah. Yep. Awesome. Bo, thanks for coming on. It's a pleasure as always. Where can the people find you? Maybe on the last slide.
Okay. Oh yeah, I'll go back to the last slide.
There we go.
Yeah. Just find me at 0xshake on Twitter, and then our organization Twitter is at Polymer_Labs, and our website is up there as well.
Awesome. Thanks, Bo.
Awesome. Nice.